Welcome to Molecular Orbitals. This lesson is going to serve as an introduction to molecular orbital theory. We're going to talk about what molecular orbitals are and how they're formed from atomic orbitals. Let's begin by reviewing a little bit about atomic orbitals. So first of all, atomic orbitals are regions of space, the regions of probability where you're likely to find an electron. And they come in different shapes. We have S, P, D, and F. Let's stick with S and P orbitals today. So, an S-shaped orbital is a spherical orbital. Very simple. A P-shaped orbital is a dumbbell-shaped orbital. Looks something like this. For the S-shaped orbital, it's centered around the nucleus, and for the P-shaped orbital, the nucleus is right here in the middle of the two lobes of the dumbbell. When atoms form molecules, they do so by sharing electrons. So if an electron from an S orbital of one atom is shared with an electron from an S orbital of another atom, they actually form a new orbital, what we call a molecular orbital. And this molecular orbital does a better job of describing the actual energies and arrangements of electrons within a molecule. Before we start talking about what these molecular orbitals look like, one of the things that's going to be really important for us to set up is how to visualize something in 3 dimensions. Because molecules are 3-dimensional in nature as well as atoms, but particularly when we put 2 3-dimensional objects next to each other, like 2 different atoms to create a molecule, the orientation of each one is going to be really important to specify. So we want to have a good way of setting that up. Because we're writing on a flat surface, we're pretty much limited in drawing diagrams that are 2-dimensional in nature. But we can still represent a 3-dimensional molecule or a 3-dimensional object. And here's how we can do that. Let's start by looking at this piece of graph paper, okay, that everyone's probably familiar with. We have a grid set up, and we can very easily set up a coordinate plane. We can put one axis going up and down. Let's say that's our y-axis, and we can have our x-axis going across like this. And we've now set up a coordinate system that can describe any position on this 2-dimensional surface. But if we take a step back from this for a second, we're going to see that this piece of graph paper is actually sitting on a 3-dimensional object, this table. Now the coordinate system we set up for this piece of graph paper is still applicable. We can still say that this dimension is our y-axis, and we can still say that this one is our x-axis. So those are still the same. But now we have a third dimension, a vertical dimension, that sort of lines up with the table here and goes up and down. And we're going to call this our z dimension, our third dimension. And by using these 3 axes, the x, y, and z axes, we have a new coordinate system that we can use to sort of describe a 3-dimensional object. Now let's see if we can map some of these S and P orbital shapes onto this 3-dimensional system we just sketched out. We're going to place the nucleus in the center of these 3 axes, and therefore when we put in our S orbital, it should be centered around that. Here's our S-shaped orbital. It's a sphere centered around the nucleus. Before we draw in our P orbitals, we should remember that for every energy level, there are actually 3 P orbitals. And now that we have this system set up for a 3-dimensional space, you might have an idea of why. There's going to be a px orbital, there's going to be a p orbital for the y-axis, and a p orbital for the z-axis. And we draw them in, they look something like this. Let's do px first. We have the one part of the dumbbell coming out like this, and the other one trailing off in the distance. For the y-shaped orbital, it's going to be the same thing. We have one coming out like this, and the other one goes towards the back. And then for the z orbital, we have one that goes up like this, and the rest of it's down that way. And so we have a 3-dimensional arrangement of 3 different p orbitals. So now that we have an idea about how we're going to draw these things, let's go ahead and take a look at how we can now combine orbitals when we're forming molecules. So the first way that orbitals can combine is when they are lined up with each other end to end. Let's look at a couple of examples of that. Here we have 2 nuclei from 2 different atoms, and we're going to look at what happens when each one it has an s orbital that it's using for bonding. So these are 2 s's, when a bond is formed between the s orbital of one and the s orbital of another, there's going to be overlap in the area between the nuclei, and it ends up looking like this. This new region represents the molecular orbital, where you can now find the shared pair of electrons. And you can see it's almost as if one of these sort of extended towards the other, and they filled in, and now we have this region here where you can find electrons. The next thing we could look at is a case where you have the s orbital of one atom joining with the p orbital of another atom. This is going to give you a situation where, again, you're going to have overlap, but the overlap is going to be in these areas. It's going to overlap between this and then this side of the p orbital, the part that's pointing towards the s orbital of the first atom. And that will result in an area that looks something like this. This molecular orbital represents the region where you're likely to find the shared pair of electrons from joining an s to a p orbital. Lastly, we could have two p orbitals that are overlapping with each other. You have your region of overlap is going to be between this side and this side. They're going to overlap with each other. So the molecular orbital that would form from the overlap of these two p orbitals would look something like this, where there's a much larger region in between the part that got overlapped versus the remainder, the other two lobes that are left out that were not involved with the bonding. Now for these p orbitals, I didn't draw in where the nuclei would be, but they would be right here, 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 and here. Those would be the locations of the nuclei for the two atoms before and after they form a bond. Now notice in all of these cases, the region of overlap was directly between the two nuclei. That's because the orbitals were considered in line with each other. So we have an in-line overlap of orbitals to create the molecular orbitals we see here on the right. Each one of these is referred to as a sigma bond, or a sigma molecular orbital. Sigma bonds occur when two orbitals are lined up and overlap to create a bond. As a rule of thumb, any time you have a single bond between two atoms, that single bond is a sigma bond. So the question is, what kind of molecular bonding or molecular orbitals are created when we have multiple bonds in the molecule? Because we know that all single bonds are simply sigma. So let's look at the molecule for C2H4. C2H4, the Lewis structure, looks like this. We have hydrogens attached to a carbon, the carbon's double bonded to another carbon, and then that one has two hydrogens coming off of it as well. We can tell very quickly that this exhibits sp2 hybridization for these bonds in this molecule. So when we look at the electron configuration for one of these carbons, we're going to see that it has a 2 sp2 orbital, another 2 sp2 orbital, another 2 sp2 orbital, and then finally a 2p orbital that is not involved in the hybridization. There's going to be one electron in each of these orbitals, hybridized or not. Attached to this carbon, the one that I circled, there has to be a hydrogen, and a carbon. Let's say that the first hydrogen forms a sigma bond with this first orbital. The second hydrogen forms a sigma bond with this sp2 orbital, and the carbon forms a sigma bond with this one. That still leaves one electron, the 2p electron, alone. Well, we know the carbon needs to make a double bond, so that means a carbon is going to also go with this 2p orbital. Now, why did I do this arrangement? Well, if we draw the three-dimensional structure, we'll see what I'm talking about. Here are some x, y, and z axes drawn in so that we can look at the two carbons and see where their orbitals are and how they line up. So the carbons are at the center of each of these axes. Now because I'm drawing this, I can choose the orientation. And I'm going to show that this 2p orbital is going to be on the z-axis for both carbons. So here's my 2p on the z-axis of both of these carbons. So these are both pz orbitals. Now I know that there's a sigma bond between each of these carbons, and it comes from the sp2 hybrid orbital. So I'm going to just draw one of those just for the sake of showing the relationship between the two carbons, and we're going to ignore the hydrogens for now. So here is an sp2 hybridized orbital from one carbon. Here's an sp2 hybridized orbital from the other carbon, and we can see that there's a sigma bond overlap in the middle that bonds these two together. This is our sigma bond, our sigma molecular orbital created from these two overlapping. Now what happens with the p orbitals though? The p orbitals are actually able to overlap in parallel, meaning the top portion of this pz actually creates a sort of a bridge here and overlaps with the top portion of this pz orbital over here. And we get the same thing happening with the bottom lobes. So now these pz orbitals have created a different kind of molecular orbital between them because they're not lined up. They are not pointing at each other. They're actually creating an orbital in parallel. And when that happens, we call that a pi bond. And this is the other kind of molecular bonding that can happen, the other kind of molecular orbital that can form, sigma and pi. So to recap very quickly, if we look back at this molecule, all the single bonds have to be sigma bonds. And one of the bonds, the first bond between the two carbons, is also a sigma bond. But the second bond that occurs, and if there was a third bond, the third bond, have to be pi bonds. This wraps up our introduction to molecular orbitals and molecular bonding. Any questions you have from this, write down in your notes and bring them with you to class.